Okay, hello everyone and welcome to the first video in this series that looks at the applications of differentiation. We have a few topics here to go over. If I get this going. Okay, we start with tangents and normals, look at rates of change, stationary points, types, min, max, because a lot of applications of differentiation is going to be related to either special cases when the derivative is zero, which implies that rate of change is zero, or we're finding rates of change at very particular times, so we're using the derivative a lot. So all of these exercises can be tied down to, are we dealing with a special case when the derivative is zero, or are we dealing at some other different time? We're going to get straight into it and look at tangents and normals, but the other thing I want to say is that most of the stuff we've covered in class, either this year or last year, it's come up in various questions, but this is now tying it all together. So hopefully we should be pretty good at it. So first off is equations of tangents and normals. Now we know the equation of any straight line can be given, we can find it using y minus y1 equals mx minus x1, where y1 and x1 are the coordinates of that line and m is the gradient of that line. If we substitute those in, we can then rearrange into the standard y equals whatever we're going to get when we rearrange it. So when we want to find the equation of a tangent, well, we can find the gradient of that line, that tangent, using the derivative. So if you're ever asked to find the equation of a tangent, we go through three steps. First off, you want to differentiate the initial equation you're given. So in this case, we were given f of x is equal to x squared. So you want to differentiate that. So we'd get f dash of x is equal to 2x. Then you're going to substitute in the given x value of where you want to find that equation of that tangent. So we might be told that that is -1. So we're then going to do step 2 is f dash of -1. And that's going to give us -2, which is the gradient at that point. And so we now know m, back in this situation over here, we now have a value for m. We have m is equal to -2. And then lastly, we have to actually substitute in the coordinates we're going through at that point. So as it says here, if sometimes you're only given just the x coordinate, this is where you need to be clear on what is f of x and what is f dash of x. You might need to substitute that into the original equation, which is f of x, to find the y coordinate. So again, in this case, we aren't given a y coordinate, but we could find it by substituting -1 into f of x. So we're going to get f of x, f of -1 is going to be -1 squared is just 1. So now we know m is -2 and our coordinate that it goes through is -1, 1, and we can substitute those in and get y minus y1, which is 1, equals -2 bracket x, take away, and our x coordinate was -1. And then just rearrange and simplify to get y equals whatever the equation of the tangent is. We can also apply that, we can use that whole process as well, but to find the equation of the normal. So a tangent just touches the function. A normal is perpendicular to the tangent. So it's at 90 degrees to the tangent. And that means the gradient of the normal is equal to -1 over the gradient of the tangent. So to find the equation of the normal, you first have to find the gradient of the tangent and then use this equation up here to get the equation of the normal. And we have done this before, so I'm going to fly through this. And the rest of the steps are the same. Substituting the coordinates into the equation of the line, general form equation line, and then you can solve to find the equation. So let's jump straight into an example. Now I'm going to do this first example all by hand, and then a bunch of following examples do the differentiation substitution using CAS, and then there's even a shortcut in the CAS which is actually already up on the screen for some equations. So we've got the equation and we're told at point x2. So step 1, I'm going to find the derivative. So y dash is equal to 6x squared minus 2x on 4. Yep. which I'm just going to simplify to y dash is equal to 6x squared minus half x. Y dash of 2, so the gradient at the point 2, we want to find our m value, is 6 by 2 squared minus half by 2 is 6 times 4 is 24, take away 1 is 23, so that's my gradient. The other thing, because I'm only told the x coordinate, I need to find the y coordinate. So y of 2 is equal to 2 by 2 cubed minus 1 on 4 by 2 squared. 2 cubed is 8, times by 2 is 16, take away 2 squared is 4, divide by 4 is 1, is 15. Okay, so I have my 3 key points. I have m is equal to 23, and I know my coordinate is at 2, 15, and I can substitute that into y minus y1 equals mx minus x1. So I get y minus 15 equals 23 bracket x minus 2. I get y minus 15 is equal to 23x minus 46. Y is equal to 23x. Add 15 to that. That's going to be negative 31. And there we go. There's the equation of our tangent. We found the gradient, m, over here. We found our y coordinate. We've given our x coordinate, and it's just a matter of substitution. Okay, same thing over here. Find the equation of the normal to the curve. Y is equal to blah, blah, blah at the point x equals 1. So the first thing I need to do is, just as a practice, we're going to do a calculation. We're going to differentiate. And that's gone in the wrong spot. Error. I want it down there. Action. Differentiate x to the 3 plus 2x squared. And you'd actually do this by hand quicker than probably this question by putting the calculator, but I want to do it anyway. So y dash is equal to 3x squared plus 4x minus 5. So now I need to find y dash of 1. Okay. Am I going to define that to do the substitution? No, I'm not. That's a waste of time, but we can get 3, 1 squared plus 2, 1 minus, that's the 4. So that's equal to 3 plus 4 is 7 minus 5 is 2. So that's our gradient. And then we need to find y of 1. Same thing. So 1 plus 2 is 3, take away 5 is negative 2. So that's our y of 1. I was just substituting x equals 1 into that. So it follows on, we get the equation. Ooh, and I've almost made an error. We're asked to find the equation of the normal. So this 2 that I got here, that was the gradient of the tangent. That was equal to gradient of the tangent. Now I want the gradient of the normal, which is equal to negative 1 divided by the gradient of the tangent, the negative reciprocal. So we get negative 1 on 2. I'm just substituting that in. So now I can find my equation using y minus y1 equals mx minus x1. So I get y minus negative 2 is equal to negative half x minus 1. So I get y is equal to negative half x plus half plus, no, take away 2 is minus 3 on 2. Doing all the algebra quickly. You can do it on your CAS if you want. Do the expansion and rearrangement to double check, but that's what it should be. Here's another one. Okay, now to point out, if this was done by hand, we're finding tangent, we've got log e to the x squared minus 1. So if this was tech free, we need to recognize that this is a composite function. So we'd have to use the chain rule to differentiate this. So I'm just going to do that quickly for you and then leave the rest of the problem for you to do. But I'm going to let u equal to x squared minus 1. So it follows on that du dx is 2x. And if we have done u is equal to x squared, we get y is equal to log e of u. So dy du is equal to, the derivative of log is 1 on u. So it follows on that dy dx is equal to du dx times by dy du. So we get 2x times by 1 on u, which is equal to 2x on u. And now we just need to resubstitute this up the top back in to get it as 2x on x squared minus 1. That's our derivative of all of that. Then you need to sub in x equals 2. You also need to sub in x equals 2 into the original function to find out what your y value is and then go from there. But I'm going to leave the rest of that problem for you to do for the sake of time. Same thing here. We have a product function. We have x times by e to the 2x. So we have to use the product rule. And then to do the derivative of e to the 2x, you could also use the chain rule just to get the derivative of that point. So this problem by hand could be very complex, or at least a fair bit of work. But I'm going to again leave that problem for you to have a go at. And I'm going to show you in a second how to check these really quickly with your calculator. But before I do that, sometimes you run into a problem where, in this case, find the equation of the tangent of the curve x to the power of 1/3, where x is equal to 0. Now, if you find the derivative of that, which is here, 1/3 x to the negative 2 on 3, and then graph this derivative, you will see it has an asymptote at the point x equals 0. And if you try and substitute x equals 0 into that, or solve, it's undefined. You can't do it. So we have a bit of a problem. Now, why is that problem arising? Well, if you also graph the original function, okay, this original function, it actually looks like this. Okay. And if you look, well, x equals 0, the tangent is going straight up and down. It has a gradient of infinity, maybe. It's undefined as like, well, what is the gradient? It just goes up for no run. So technically infinite, possibly. So you then have to just realize, okay, what's the equation of a line straight up and down? Well, a line straight up and down at x equals 0 is just x equals 0. That's the equation of the tangent. So we can sometimes run into problems like this where you need to graph the original function and then go look at what this special case is at that point. But I said I was going to show you how to do these via CAS. Okay. You can get into this by, there's two commands. There is the tan line command or the normal command. You can get into these via either the action or the interactive. I think the interactive menu is better because it's going to give you the pop-up and remind you what are the things that you need to enter. While if you do the action menu, and if we just do this quickly, calculation, line, tan line, now you have to remember what you need to fill into there. So what happens if you just put the equation? You're going to get an error. What if you put the equation and then variable x, you still get an error because you need to tell it what's the equation, what are you going to differentiate with respect to, and then what's the x coordinate of the point you want to find the tan line at. So that's why I like interactive, calculation, line. We can do tan line, and I'm going to go back to this one here to double check. So my original expression was log natural, or log to the base e of, I need to put the x in, x. Calculator's having a bit of a brain fart. X squared minus 1 the variable that this equation has is x. Bracket button there. And what was the point we were asked to find? Well, it was at x is equal to 2, and we just hit OK, and it fills in the equation for us and finds the equation of the tangent. It turned out the equation of the tangent at that point was 4x on 3 plus log to the base e of 3 minus 8 on 3. So a bit of work, that's what the eventual answer you're going to get using this derivative. But that's how you can check really, really quickly what the equation of the tan line is, and same for the normal. It's also there. Interactive calculation line, normal. And why didn't you do that? There we go. Sometimes my pen on this CAS simulator plays up. So same thing, we can put in the expression. So let's check our work here. This was x. Hasn't gone in. This is x to the 3 plus 2x squared minus 5x, and we were doing it at x is equal to 1. Oh, that's put it in front of the other command. Need to drag it down there. There we go. Negative x on 2 minus 3 on 2, which is what I got. So that's how we can do it on our CAS. So really nice and straightforward. So if it's tech active, even though up here in this problem, even I found this derivative using the CAS, and then I could have defined it and done the substitutions. While that's all well and good, if you have a CAS active exam and you need to find the tangent of the normal, you are insane not to use these two commands. It's completely expected to use these two commands. They have similar commands on the other type of calculator. You're just wasting your time and energy if you try and do it or show more working. Literally, it could be a 1 marker. This could be a 1 marker. If you're asked a question like this, your answer is just straight from the CAS. That's it. There's no other required working, I would say. That's it for exercise 10A, and I'll leave this video there. As always, if you have any questions, comment below or shoot me an email.